electronic skin, e-skin, materials, sensing mechanisms, and emerging technologies for healthcare applications. Electronic skin, e-skin, is a class of bio-inspired, flexible electronic systems designed to emulate the multifunctional sensing capabilities of human skin, including the perception of pressure, temperature, humidity, strain, and biochemical stimuli. By integrating advanced materials, microfabrication technologies, and intelligent data processing, e-skin enables continuous, real-time, and non-invasive monitoring of physiological and environmental signals. These capabilities have driven rapid development in applications spanning healthcare, prosthetics, robotics, human-machine interfaces, and personalized medicine. Human skin, the body's largest organ, provides a unique combination of mechanical robustness and multifunctionality. It acts as a protective barrier while enabling complex sensory perceptions such as tactile force, heat, humidity, and pain. Replicating these properties in artificial systems has been a long-standing challenge. Early efforts in the 1970s focused on flexible electronics with rudimentary tactile sensing, laying the foundation for modern e-skin technologies. Recent advances in nanotechnology, materials science, and flexible electronics have significantly enhanced e-skin performance, enabling multimodal sensing, high sensitivity, and conformability. The emergence of artificial intelligence, AI, the Internet of Things, IoT, and wearable healthcare systems has further accelerated innovation, allowing e-skin devices to process large datasets and provide predictive diagnostics. Modern e-skin systems not only mimic biological sensing but also incorporate additional functionalities such as self-healing, energy harvesting, and wireless communication, thereby surpassing natural skin in certain aspects. Design requirements and functional attributes. For effective long-term use, especially in healthcare monitoring, e-skin must satisfy several key requirements: mechanical compliance and flexibility. E-skin must accommodate large deformations such as bending, stretching, and twisting without loss of function. Strategies include the use of intrinsically stretchable polymers and geometric engineering of rigid components, such as serpentine interconnects. Conformability and adhesion. Intimate contact with irregular skin surfaces enhances signal fidelity and reduces motion artifacts. Ultra-thin, soft materials with low elastic modulus enable seamless integration with biological tissues. Breathability and comfort. Porous structures and permeable substrates facilitate moisture and gas exchange, preventing skin irritation during prolonged wear. Biocompatibility and biodegradability. Safe interaction with skin and environmentally sustainable disposal are critical. Biodegradable polymers and transient electronics are emerging solutions to reduce electronic waste. Multifunctionality and stability. E-skin should integrate multiple sensing modalities while maintaining long-term operational stability under repeated mechanical stress. Advanced materials for e-skin. The properties of its constituent materials fundamentally govern the performance of e-skin. Typically, e-skin systems consist of flexible substrates combined with functional, active, materials. Substrate materials. Common substrates include elastomers such as polydimethylsiloxane, PDMS, polyurethane, PU, and thermoplastic elastomers, as well as flexible polymers like polyethylene terephthalate, PET, and polyamide, PI. These materials provide mechanical flexibility, optical transparency, and chemical stability. Emerging materials include hydrogels and organogels, offering tissue-like softness, high water content, and ionic conductivity. Biopolymers, for example, silk fibrine, cellulose, chitosan, enabling biodegradability and biocompatibility. Self-healing polymers, incorporating dynamic covalent bonds or supramolecular interactions to repair mechanical damage. Functional nanomaterials. Active sensing layers rely on conductive and semiconductive nanomaterials, metallic nanostructures, Ag, part nanoparticles and nanowires, carbon-based materials, carbon nanotubes, graphene, reduced graphene oxide, semiconducting nanowires, silicon, zinc oxide, and conductive polymers, for instance, PEDOT, PSS, polyaniline. These materials provide tunable electrical, mechanical, and optical properties. For example, graphene-based hybrid nanostructures have demonstrated extremely high gauge factors, up to approximately 320 at low strain, enabling ultra-sensitive detection of subtle physiological signals such as pulse and facial motion. Structural engineering. Micro and nanostructuring plays a critical role in enhancing sensitivity and functionality. Examples include porous and hierarchical architectures for enhanced compressibility, microcrack and interlocking structures for strain amplification, bio-inspired designs, for instance, fingerprint-like patterns, for improved tactile sensing. Sensing mechanisms. E-skin devices employ several transduction mechanisms to convert physical stimuli into electrical signals, piezoresistive sensing. Piezoresistive sensors operate via changes in electrical resistance under mechanical deformation. Conductive networks within elastic matrices, for example, CNT polymer composites, gold nanowire networks, enable high sensitivity and wide strain ranges. For instance, gold nanowire-based sensors exhibit gauge factors approximately 9.9, stretchability greater than 350%, and rapid response less than 22 milliseconds, suitable for motion and pulse monitoring. Capacitive sensing. Capacitive sensors detect changes in capacitance caused by variations in electrode spacing or dielectric properties. CNT-based and textile-integrated capacitive sensors demonstrate high sensitivity, fast response, less than 10 milliseconds, and excellent durability, greater than 10,000 cycles, making them suitable for wearable electronics and e-textiles. Piezoelectric sensing. Piezoelectric materials generate electrical signals in response to mechanical stress, enabling self-powered sensing. Flexible piezoelectric materials such as poly, L-lactic acid, nanofibers and bio-derived gelatin nanofibers offer high sensitivity and long operational lifetimes, greater than 100,000 cycles. These sensors are particularly effective for dynamic physiological monitoring. Triboelectric sensing. Triboelectric nanogenerators, TENGs, utilize contact electrification and electrostatic induction to convert mechanical energy into electrical signals. These self-powered systems exhibit high sensitivity and fast response, approximately 68 milliseconds, and can detect pressure, sliding, and complex tactile interactions. Bio-inspired designs have achieved spatial resolution exceeding that of human mechanoreceptors. Multifunctional and intelligent e-skin. Human skin simultaneously senses multiple stimuli. Thus, multifunctional e-skin is highly desirable. Integration of different sensing mechanisms enables simultaneous detection of pressure, temperature, strain, and biochemical signals. For example, hybrid nanofiber systems combining piezoresistive, piezoelectric, and triboelectric effects can independently detect force and curvature with high sensitivity and stability, greater than 60,000 cycles. Spatial resolution is achieved through high-density sensor arrays, often fabricated via cross-stacked nanofiber networks or microfabrication techniques. These arrays enable precise mapping of pressure distribution and motion. Integration with AI and machine learning enables advanced data processing, allowing real-time health monitoring and predictive diagnostics. Deep learning algorithms can analyze complex multimodal datasets, improving accuracy beyond traditional analytical methods. Health monitoring applications. E-skin plays a transformative role in healthcare by enabling continuous monitoring of vital signs. Body temperature. Flexible thermal sensors provide real-time monitoring, overcoming limitations of conventional thermometers. Respiration. Strain and pressure sensors detect respiratory rate, 12 to 20 breaths per minute in adults, depth, and patterns, enabling early detection of respiratory disorders. Pulse and blood pressure. Wearable e-skin can monitor cardiovascular activity, critical given that cardiovascular diseases account for over 17 million deaths annually. E-skin also enables monitoring of muscle activity, oxygen saturation, and biochemical markers, supporting early diagnosis and personalized treatment. Energy harvesting and wireless communication. To achieve long-term operation, e-skin systems increasingly incorporate self-powered technologies, mechanical energy harvesting, via piezoelectric and triboelectric nanogenerators. Thermoelectric and photovoltaic systems, for harvesting body heat and ambient light. Wireless communication technologies such as RFID, NFC, and Bluetooth Low Energy, BLE, enable real-time data transmission to external devices, facilitating remote healthcare monitoring and telemedicine. Organic Thin Film Transistor, OTFT, based e-skin. OTFTs offer a promising platform for large-area, low-cost e-skin fabrication. Their intrinsic signal amplification enhances sensitivity and signal-to-noise ratio. Additionally, OTFTs enable seamless integration of sensing and signal processing, paving the way for fully integrated, smart skin systems. Despite challenges such as lower carrier mobility compared to inorganic semiconductors, ongoing advances in organic materials and device engineering continue to improve their performance and stability. Emerging trends and future perspectives. Recent research is focused on advancing e-skin toward more biomimetic and sustainable systems. Self-healing e-skin, utilizing reversible chemical bonds for autonomous repair, biodegradable electronics, reducing environmental impact and e-waste, neuromorphic e-skin, integrating artificial synapses for tactile perception and learning, energy autonomous systems, combining sensing and energy harvesting, hybrid bioelectronic interfaces, enabling direct interaction with neural systems. Additionally, the integration of soft robotics and prosthetics with e-skin is enabling advanced human-machine interfaces with sensory feedback. In conclusion, e-skin represents a rapidly evolving interdisciplinary field at the intersection of materials science, electronics, and biomedical engineering. Advances in nanomaterials, flexible substrates, and sensing mechanisms have enabled highly sensitive, multifunctional, and wearable systems capable of real-time health monitoring. Despite significant progress, challenges remain in achieving long-term stability, large-scale manufacturability, and seamless integration of sensing, energy, and data processing components. Continued research in advanced materials, device architectures, and AI-driven analytics will be essential to realize the full potential of e-skin in healthcare, robotics, and beyond. Overall, e-skin is poised to play a pivotal role in next-generation wearable technologies, offering unprecedented capabilities for personalized medicine, human-machine interaction, and sustainable electronics.